Hi, this is Bill Foote, and in this episode, we put it to the test. We're going to compare and contrast the two most contentiously, they beat each other up, approaches, two most contentiously approaches that we've been using for years. One is the textbook conventional approach with Ronald Armile Fisher on board, uh, which really requires a central limit theorem, a repeated sampling, um, which in life, I have not seen that very much even possible. It's very expensive for one thing. And the other is a Bayesian approach, which allows for, yeah, lots of data, but not necessarily repeated sampling. I'm thinking of economic data, for example. Each datum is very likely an independent sample of size 1 every single time that we use it. But we pretend that maybe a time series is repeated sampling, but it actually isn't. I digress. First, two hypotheses, and it's a tale. So the idea behind Bayes is flipping the script. If P is a probability, or PR is a probability of data given a hypothesis, that's what this expression means. That's a conditional hypothesis. How do we flip it into the probability of a hypothesis given data? And after all, that's what we're really after. That's really kind of where what we would like to say as decision makers. This is called the posterior probability. Bayes' rule is exactly this. And we could do it for hypothesis 0, or hypothesis 1, or hypothesis 21. And we can have as many hypotheses as we want. And it's really a ratio of the probability of that hypothesis relative to the probability of seeing all the data associated with that hypothesis. And here again, the probability of the hypothesis, 1 in this case, relative to all of the probability of all the data. It's a relative probability. I hope the idea of odds might come to you. And in fact, if we divide one by the other, and here we are doing the probability of H1 given D divided by the probability of H0 given D, we see that we have ratios of two hypotheses. Okay, and this piece here, the probability of data given one hypothesis divided by probability of data given the other hypothesis, is called the Bayes factor. And this multiplies the prior odds ratio, and we get a posterior odds. Okay, that's a little murky idea, but we'll hold it for just a second. Okay, what do the posterior odds tell us? It records the relative discernibility, compatibility, consistency of the hypothesis with the data, relatively. It's one or the other. And we've chosen here uh, something that at least can align with one of those methods. One method is called the frequentist, and H0 is often called the null hypothesis. To me, it's just any hypothesis. It doesn't matter what it is. On the far right, we have prior odds. And this is what we believe about the two hypotheses, one versus the other, in odds form, which is a ratio form, 3 to 1, for example, uh, or 1 in 3 even, before applying the data. And then in the middle, we have Bayes' factor, which is the relative evidence. So we have relative beliefs times relative evidence, giving us relative conclusions about the consistency of one versus the other. Consistency of hypothesis 1 versus hypothesis 2, consistency of what? The hypotheses with data. If this works out to 3 to 1, then we would say hypothesis 1 is 3 times more consistent than the hypothesis 0, given the same data. That's all that means. It's very simple. It's used by bookmakers, traders, people in normal commonsensical language. Often in studies, the Bayes factor is the only thing that is actually talked about. And we got to talk about something here. We're going to frame hypotheses in a binary sense, mutually exclusive, completely exhaustive. We're going to look at all the possible hypotheses. Okay, if we have one hypothesis, we have to look at least at its opposite. Okay, so that's where we start. Just two, binary. Either one hypothesis or theory or conjecture is true, the other is false. And that's how most people believe things. Actually, the world is, I mean, that's just two things going like this at each other. But actually, things are probably overlapping. Okay. That's very quantum of us. Double slit experiment-wise in making decisions. But we're talking about virtually true or false. And the virtual unconditioned statement, yes, this is true, that's false. It's virtually unconditioned because at this moment in time, we have sampled, our sampling hamsters have just gone, we've had enough. Or we've simply run out of funds. We cannot even go any further. We have no recourse at this instant. We're finite human beings, and we run out of even time, money, space, interest, exhaustion, something. We've run out of something or everything. Okay. So we have no more questions to ask. The prosecution rests. The defense rests. We're done. Jury, make a decision. And the decision will be virtual. And it is unconditional in the sense of we have no more questions at this moment. At this moment. That's why it's virtual. Well, we're just looking with consistency of hypotheses or theories or conjectures with actual observed data. In fact, we might even consider that there's observed data and there's unobserved data. Our thought experiments are the list of hypotheses. And we have beliefs about these hypotheses. We get a statistical hint, I say indicator here, or even a cue, about the possible falsity of an hypothesis. Now, falsity, I don't even know if that's a real word. I've seen a falsification comes out of it. The quality of not being true. So that's like good and evil. Evil is really the condition of being deprived of the good. So we're gonna take that here as well. A lack of evidence of truth, and some theories lack more evidence than others. That's the idea behind the prior, posterior odds and the evidentiary odds, the thing called the Bayes factor above. That's statistical hints. And all of this says that knowledge is finite as of the moment. Data is observable, but you might observe other data. Theories are possibly incomplete. We might think up another idea and throw it against the wall like we would spaghetti in the old days to see if it's done. Throw it against the wall of data. And then just go back over again. The goal, however, is to deduce the impact of the hint or the cue on the probable status of a hypothesis. I don't even care about whether it's true or false at this point. It has a status. And so I want to look at hypotheses as glass half full, not glass half empty. Okay, that's where we're going. Now, if this makes any sense at all, we almost ought to use the moral should or ought here. If this is the case, then is equals ought, according to John Searle from a while back, the early 60s, which really is Thomas Aquinas, I believe, in analytical philosophy terms. Yes, logic is very important. We should use Bayes' theorem to deduce. That means use a principled, logical approach. The impact of the cue, the indicator on the status of the hypothesis. And we need all three steps to get there. Most people who do this work ignore or forget about or lightly pitter-patter over step 3. Okay, this is the step that must be done. This is the step that gave us 16%. Will give us 16% below when we go ahead and do that. Not above, it's below. Oh, here we are. So here's an example. We regularly conduct reviews of our activities, our very expensive research and development activities. We often discover things, and one of our discoveries is that there is no discovery. That's a very positive result, actually. Again, glass half full. We learn from that, and we try not to make that mistake again. But no, it's there. There's knowledge in everything. Innovation is growth, and it's the key to providing, in this case, relevant services and products for our customers, or to our customers. Which is it? It's both are dative cases. When we observe that our innovations actually meet customer needs, we will say that is, let's say, a service level of 95%. On time, in full. Like, for example, if 80% of the time the package arrives and 90% of the time when it does arrive, it's a complete package. Nothing's wrong with it. Well, that's 72%. 90 by the both and counting rule, that's 72%. That's not very good. We need 95. When we do not meet their needs, we serve only 5%. So it's 95 and 5. Okay, this 100%, right, of the customer base. Okay, and the rate at which innovations actually meet customer needs is only 1%. Yeah, we persevere, yes. What is the probability of an innovation meeting customer needs given high service levels of 95%? Yeah. So let's put this into a format here, and this is going to be doing Bayes all the way through. Probability of positive finding is positive. All right, that is this customer service rate. And an hypothesis, that the hypothesis basically is, do we meet the customer? We meet the customer's needs, and that's true. The probability of a positive given true is 95%. And we'll call that the power of the test. That's officially got a name. 95% is the power of the test. It's a tough criterion. And suppose the probability of a positive finding when the hypothesis is false is 5%. Now, we had an example like this in a prior episode of spam, no spam, flagged, not flagged, where we looked at false positives, false negatives, true positives, and true negatives. This is along the same route. This 5% is called the false positive rate. And when a hypothesis is false, but we find it to be true. Okay, imagine, again, an intrusion, a threat. The hypothesis is no threat. The positive finding here would be we got clobbered. Okay, we only want that to happen no more than 5% of the time, because we can't take any more clobberings, right? The 1 in 20 rule here. Base rate is that an innovation meets a customer's needs on the customer's own terms. And we suppose that's one in every 100 hypotheses, that it is innovations in our example turned out to be pretty true. The probability of a true as opposed to a false hypothesis is 1%. Does anybody really know what this probability is? And the answer is no. But as many researchers, and I'll just note Richard McElreath and Leipzig with his book Statistical Rethinking, it's very small. Yeah, and that's the history of philosophy. Thomas Kuhn, for example. It takes a revolution. And revolutions do not happen very often. There's one happening in economics right now, where there's going to be a revolution in the use of neoclassical models only as the primary method of modeling anything. Why? Because they don't work in certain situations. They're not designed for certain situations, and yet we apply them. Well, it's going to take a while to go through that because everybody's trained in neoclassical economics. all ideas, theories, and conjectures are not reported. We only see a few of them actually, and there's very few of them that actually survive. For example, 15% of all new business survive more than 10 years. It's a survival rate. Okay, it's pretty small, and there's some data to back this up if the site is still open. Another example, FDA drug trials have a success of 13%. It's a low number. Jointly, 15 of 30, it's really small. 2% of innovations might make it to the market. Well, so anyways, we're gonna get conservative here. Positive rate of a rate. We can change that. Now here's Bayes. Very simple. The data is positive, given it's true. Probability of true versus the probability of the data being positive. Flip it around and you get the probability of true given positive. Well, what's this probability of positive down here? It's actually an expected value, where we have something that could be true with probability and otherwise false with probability. Those two must add up to 1. And they condition this conditional statement and this conditional statement. These are the two ways things can happen. And we put them together this way. 95% of the time we have a positive, given that it's true. Okay, it works. We have a base rate of 1% that it is true. Very small base rate. And then here is the weighted average of base rate. Okay. Base rate and its complement, not base rate, which is the probability of false. And it's weighing together positives and negatives. And there we go. Very small number in the numerator, less small in the denominator. Answer is 16. Not 42. Answer is 16. And the beauty of this is if you raise that base rate up to a big number, this is still going to be a fairly small number. Maybe a coin flip, as I say right here. The false positive rate to 1% and get only a probability of 50. It's a coin flip. Okay, you can read that. It's interesting. But I want to get on to a comparison of the two approaches, which are really projects in practical epistemology. Very, very practical. We're trying to figure out what is and what isn't, probably. One of these two basically says what is and what isn't, period. It doesn't go to probably, although it tries to. There's a number in there that we try to use as probable. It basically says it's either this or that, period. And that's like a platonic form, eternally in space. It never changes, and that's just the way it is. That's a lot of the Enlightenment project was like that. Either it is or it isn't. We're saying it's something in between, as most commonsensical human beings do. But let's illuminate this a little bit. We're going to do both approaches. We're trying to support a decision about materials handling practices, and we want to figure out our worker teams going to be able to execute against these practices. Some executives claim in this case that 10% of worker teams that have enough experience not to require any further training, they're fine. And we have training all the time. I'm in the middle of required training against various statutes, trying to create a more, yes, I'm going to say, inclusive environment, less judgmental environment, and one that focuses on, again, half full, not half empty. And there's also another one I have to take on cyber, because that environment is changing very, very quickly, and we must be safe. So we get training to be safe. But some people say that 10% have enough experience. Others believe that 20% have the requisite set. Well, which is it? Either or is one way of thinking about it. Or we can think about it as a mixture of the two. Okay, it's entirely possible that they overlap, which will require further investigation. One will plausibly have more or less odds of being true as opposed to false, which was the Bayesian experiment we just went through. Okay, support a decision. Now, management knows that the highly likely uncertainty of results will allow us to be wrong 5% of the time. And this is one wrong result in 20 samplings. So we have some funds, because you have to pay people to do this. You have to take time from other opportunity cost economists, to draw a random sample from the population. We can do all sorts of latitude designs and all sorts of things to get there, but we get a random sample. And it needs to be representative. It has to go across all sorts of criteria. We need to interview people as to what those criteria should be, and we hire somebody from the outside to make sure and challenge us that we did a good job of the sampling. Travel and lodging expense into a remote regions where physical security may easily be compromised. Danger, 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 yes. A 5-person fact-finding team over a 15-day period will entail a consultant equivalent cost of $200,000 plus another $300, and on and on and on, just for the one sampling. It's expensive, especially if you have a far-flung empire of sites to visit with different cultures and people with different levels of education and experience in that mixture. But the cost of making a wrong decision here is both financially and, more importantly, reputationally. It takes years to build a reputation, a couple of seconds, nanoseconds these days, because of social media. It's accelerated this to destroy one. So this is an important decision. So let's be a frequentist. Let's set this up in a frequentist, textbook frequentist approach, like Anderson and Sweeney or Ken Black's book, or, oh, you can find it on Wikipedia. The first thing we do is we set out two opposing hypotheses. One is the null, that only 10% of workers' teams are experienced enough in hazardous materials handling. The other is that there are more than 10%. Okay, very simple. So the null hypothesis is what the first set of executives said. 10% is good enough. And H1, alternative hypothesis, it's more than that. That's the other side of the story. We then set a tolerance level for being wrong about selecting the null hypothesis as true. wrong if it's true, when in fact it turns out to be false. Okay, go back and think about what that was called. There's a rate, commonly chosen rate level of significance in Ronald R. Miles', well, I think it was 1925 manual. She was using in an agricultural context, um, almost a food engineering context, along with William R. Gossett, um, student and student-tees distribution. Was working for Guinness, the brewery, yes. 1 in 20 time rate of observing that we're going to be wrong about choosing a null hypothesis over the alternative. That is 10 versus, you see, binary, very binary. Significance level. Wrong about his alpha equals 0.5. It's often given the name alpha, but we don't need that. We sample 5 different worker teams and find 1 experienced team. The observed data is, in 5 samples, we find 1 experienced worker team. This is binary. Either you are or you aren't. So, very straightforward. We calculate now the probability that the data associated with the alternative hypothesis, namely that it's greater than 10%. For example, 20%. That there are 10% or more experienced worker teams given the null hypothesis. This probability is supposedly called the p-value, not to be confused with p equals the proportion of successes in a binomial draw, which is also known as the probability of a single success. With the null hypothesis, though, the probability of no experienced worker teams in a single sample is 90%. With the null hypothesis. See, that's the point, with the null hypothesis. Now, the p-value is calculated in this way, and it works out to be 41. It's the probability that x is greater than or equal to 1 for n equals 5, p equals the proportion in a binomial case of 10%. And that's, greater than 1. Okay, there's more than 1. X equals 1, greater than 1, which means there's 2, 3, 4, 5. Okay, up to 5. So what is the probability that it's greater than 1, which means what's the probability of it being non-null, I guess? It's hard for me to even say that out loud. Okay, now we can use the trick that the probability greater than 1 is equal to 1 minus the probability that it is 0. And that we define any experienced worker team. And that's 1 minus 0.9 to the 5th power. It's a real simple one, this one. Because you take 0.9 5 times. Okay. And that's equal to 0.41. Oh, that's good. Convince yourself of that, though. Clever use, very clever today. P-value is just the probability of observing more, and this is a really important interpretation of this thing called the p-value. Observing more extreme outcomes given the null hypothesis is true. It's 41% chance, I guess, if we count the ways, as we have been. The null hypothesis, given that a null hypothesis is true, 41 out of 100 different ways, that's a lot. It's almost a coin flip. And that's how people interpret this. We recall our admonitions, however, that we must resist the idea that this is probability of accepting as true the null hypothesis. It's not, because it's either or. Once you've made the decision of accepting or rejecting, you're done. There's no in between with this method. And that is the key point to make. Why? Because that's how it was set up. Very simple. That is how it was set up. Very platonically. And you can't even say that the probability of accepting as false The alternative hypothesis, you can't even say that. This is the probability that x is greater than or equal to 0. Okay? It had, and then that is translated into either accept or reject, given a prior view that this can be, if this is greater than 5%, then it's then we've discovered nothing. Okay, we haven't discovered anything. We keep the null hypothesis. Okay. Now, we conclude that the data do not provide evidence that the proportion of experienced workers is greater than 10%. And if we had to put between 10 and 20, even though this hypothesis does not actually in any way confirm this null hypothesis, we will likely stick with the 10%. Again, think of this. You're already talking probabilistically, and you're not supposed to. Right? So this is the notion of falsification. We're falsifying the idea that it's 20. Or we're falsifying the idea that we should consider anything other than 10. We're not even talking probabilistically here. I think I've beaten that horse to death. Poor baby. And yes, indeed. Now, on the Bayesian side, we construct a grid of alternative, mutually exclusive hypotheses. We can start with a grid with 5% work in increments up to, for example, 50% unobserved proportions of experienced worker teams. This is the conjectures. This would have us list 10 equally spaced vertices, nodes, and 9 edges, intervals, and we could go ahead and do that. And this is different than building a null and alternative. So we're going to call it H1 and H2. H1 will be the proportion is 10%, binomial proportion is 10%, and H2, the binomial proportion is 20% worker teams. Okay, that's all. And they're agnostically alternative. They're mutually exclusive. Okay? But they may share information between the two of them. I don't know. We'll have to see. Initially, we don't care one way or the other about them, so we'll give them an equal probability. Probability of one is the same as the probability of the other. It'll be 50-50. So we have two hypotheses. Not a null, which is, to falsify any idea that it could possibly be 20%. Again, possibly. Again, it's possibility, not even probability. So that's more of a possibility score, I guess, the p-value. P for possibility. No, not quite. I don't have a word for it yet. Nobody seems to have a word for it yet. Our observed data is exactly the same. We're going to use the same binomial model. Either E or not E is true. Experience or not experience. Repeated sampling. There's not too much sampling here. There's only 5 samples here. Okay, so typically you have to take this a lot longer than that. And we can express this as E is simulated, if you will, using the binomial distribution, and P, the proportion of a single binomial trial, one binomial trial, is uniform 0, 1. Okay. You can play with this with some interesting software too, by the way. We're going to say that, very simple, that P is simply 50-50. Okay. It's the mean of the uniform distribution between a 0 and a 1. Okay. Very, very straightforward. Yes, you can have uniform distribution, say, between 20 and 35, okay? But this is between 0 and 1, like probability. The likelihood now. That's the next thing we're going to do. The cross hypothesis likelihoods are mutually exclusive but do not add up to 1. They can't. They're a likelihood of an hypothesis given all the data. And that situation is going to be radically different, mutually exclusive, remember, than the other hypothesis given all the data. They're two very different beasts in the animal, plant, and fungal kingdoms. Okay, very, very different. And here we go. So this looks binomial to me. Oh, that 41 is coming back. The probability that x equals 1, that you have one success, one experienced, given the first hypothesis, which means that the proportion of experience is 10%, is 5 choose 1, 10% raised to the 1 power, only happens one time. The other four paths are at 90%, 1 minus 0.1. We do all of this and we get 33%. That's the score. And for hypothesis 2, the only thing that changes here is the 20, 80. 10, 90 become 20, 80, and you get 41%. Now, the posterior, okay, of these, this is data given an hypothesis. We want to flip the script, as we said before. Have the probability of H1 given the data, probability of H2 given the data, given this. And that's pretty straightforward. If we look down here about how to do that, we use Bayes' theorem. And it's very straightforward again. From our very first example, this is the last step. People typically just do this. They don't go to this last step where they now say, and this is what we really want to know. This is the evidence here. We got the evidence. It's 33 and 41. But the base rate is probability of H1. Okay, that's 50%. That's the evidence, 33%. And then we look at that evidence and the other evidence, the other hypothesis, because they're sharing information, literally. Their distributions can possibly overlap. And 50-50, that's the expected value, if you want, of the evidence. That's what that probability means, the expected value of the evidence. And it works out to 44. Now, if we do the same thing, using a complementary trick, it's 56. Because we have 50, 41 across the same expected evidence. 44 and minus 44 or 45 is 56. I did some rounding there, I guess. Okay, they're pretty close together. That's what you got to say. The two hypotheses are close together. They mix. That's what this thing says. It's not the frequentist conclusion that they are radically different. I really didn't discover anything. What did I pay you for? I already knew that, is what one of the executives might well say. And we have a table here. Oops, sorry about all of that. Oh my goodness, look at this. Yes, this is all in, this is a plug for doing R. Okay, here's the table. So, I built a small table. I have seen this table in a couple of places. I feel like I invented it because I worked so hard to produce it, but I did not invent it, I do not believe. And I do not know the source. And if you're listening to this, you are the source. Let me know and I'll be happy to throw your name in here and change everything. Okay, so we have these different situations. We have low sample, high samples. Everybody's going to say academic journals and say, you didn't draw enough samples. Right? Okay, fine. Okay, I didn't draw enough samples. Okay. So here's the probability. 10% experience given nx. You can compute this. Okay, with h. Right? And if you go up here and see what h is, okay, that's the hypothesis that it's 0.1 or 0.2. And then x or more, 10%, that's the 0.1, that's the frequentist approach. You see that 44 increase the size, it goes up to 59, and if you find 3 teams in 5, or 3 teams in 10, it's the same sequence, low to high. And notice what happens on the flip side if you were to use the hypothesis 20% instead. That's the alternative. It really should have been a line here. It's just the flip of this, as is when you increase both the number of successes, experienced teams, as well as the size of the sample. You get the same pattern, exactly the same pattern. Now, with the frequentist approach, we get something a bit anomalous, I believe. So the hypothesis is, this is all they're worried about is the null hypothesis, 0.1, or greater than that. Okay, probability of that given 10% are experienced. Okay, fine. But it's actually flipping around. It's that evidence approach, pure evidence, without going and flipping it to find out how does that evidence, which is NX, actually influence. Okay. So here we get 41, and here we get 65, and here we get 1, and we get 7. Okay. And if we had set up our value to 0.2 over here, what would we get? We probably would get something different. What a wonderful exercise to do that. And what we're doing is we're showing the degree of sensitivity of the frequentist method to what the null hypothesis is. Tremendous sensitivity to whether this is 0.1 or, and if you put 0.2 in here, see, and tremendous sensitivity here to size. Okay. Here you get basically the same thing. They split. Okay. They basically split here. Yeah, 44 to 56, 59 to 41, 14 to 86, 22 to 78, and here we get 41, 65, 1, and 7. This is very, very sensitive to the size of this given the sample. In other words, you can hack this down simply by getting more data. And I think that's been one of the major issues with the frequentist approach in certain situations. Just get more data and bring this thing right down. Right? Make it more or less. This actually flips it. This basically says that if you get more data, or on a 3 and a 3, you have to trash the null hypothesis. That's what it says. That p-value is low. These p-values are high. These just flip around back and forth. They're not p-values. They're degrees of lumpiness, if you will, of a hypothesis, one versus the other. 14 to 86, 22 to 78. So let's be clear about what happened here. As we increase sample size, we get this, and then we get this. And we increase it again, we get 14 to 86 and 22 to that. Okay. So roughly the same idea. Roughly the same idea. As we increase sample size with the frequentist approach, look at what happens. Increase sample size. We get 41 to 65, and we go 1 to 7. But if we increase this, we have a much higher ability to flip the script. We start accepting the so-called null hypothesis and rejecting. These are an acceptance of the null hypothesis. These are rejections of the null hypothesis. The story has flipped. But the Bayesian doesn't care about that story. And we can go further and talk a little bit about some of this, and oh, you can play with this all you want. And some of it is this problem. To a frequentist, certain statements are absolutely forbidden within their framework. The judgment, the theory is true, is not a repeatable event. That's why. And it's true also for the Bayesian, but the Bayesian goes, yeah, why it might not be repeatable, and that's true, but it might become more plausible with more data or a change in the way we think about the data. And those are the conjectures and the probability of the conjecture. So it allows for a further discussion. In a sense, the frequentist approach is done and dusted. Okay, that's the idea there. And the thing is, most people would rather talk about the probability that the hypothesis is true, null or alternative. They don't care. They're just two different possibilities. The current situation or an innovation. And the degree of difference between them, if we just take the difference, we wash out a lot of the information between them. But if we take them separately and compare them separately, like we did with the increase the number of trials from 5 to 10 in the table above, then we get something very interesting. Down here with the possibility of how to interpret this is from the U.S. Bureau of Labor Statistics, and it regards confidence intervals. The intervals within which, at a level of probability, we can expect to find our estimate of, in our case, proportion of workers who are experienced. There's both sampling and non-sampling error. In the sample area, we can, with a BLS survey, look at an entire population survey, but we're not actually looking at an entire population. We're looking at a sample of the population. And is it a representative sample is the other issue. Okay, maybe the design of the sample is not sufficient. And for them, they use a 90% chance or level of confidence. We don't use the word confidence in Bayesian because it's just about consistency of data with hypotheses. That's all. I don't have confidence one way or the other. Tolerance, none of that's in that way of thinking, the Bayesian way of thinking. But it's all over the frequentist way because it's one or the other. An estimate based on a sample would differ by no more than 1.6 standard deviations from the true population value because of sampling error. The BLS are generally conducted at this level of confidence. So they have an idea of a sample from a population, and the whole point of their analysis is to say how representative is the sample of the population when you really don't know the population. And there are all sorts of epistemological problems with that statement alone. They give an example straight from the BLS. Let's see. Yeah, that's where it is. I'm wondering if this link still works. Yeah, there it goes. And this is a technical note from them. Okay, so that's always a good thing to read. And as we go on and try to finish this piece, it will finish someday, it would seem. A little bit of confusion about this table, but knowing here that this is a flipping of their conditions here. More data basically says, here more data says you know, more null hypothesis, and this one here is basically saying null hypothesis, and here's where it flips. That's the piece I wanted to get to. It flips. It says 5% is enough to keep the null hypothesis with more data. Here's less data, and you're trashing the null hypothesis. Okay, it's confusing because it flips. But then we go back to the BLS, and in this particular one, we have a monthly change in total non-farm employment. There's a survey, plus or minus 110,000. You see why there's revisions, because it's a survey, and people eventually respond, and they come back and they revise, and so on. And this 90% confidence interval is going to be from minus 60,000 to 160. It's 50 plus or minus 110. Okay, and it doesn't mean they're off by this, but that there's and here's a Bayesian approach to thinking about it. There's a 90% chance that the true over the month change lies within this interval. That's a good way of thinking about it. From a Bayesian point of view, that's a perfectly valid way of thinking about it. It is likely that non-farm employment had in fact risen, and that's what they're saying. But the frequentist statistician, which is all the BLS people, this is not what it actually means. I spoke that as a Bayesian. The only thing that they can say is what's right here. The only cannot tell you there's a 95% chance that a real change has occurred, because that's not the kind of event that frequentist probabilities may be assigned. Ideologically bent frequents, this is meaningless. They're talking as Bayesians when they actually did a frequentist discussion of the range of that data. Here they use a p-value. We assume that H0, the null hypothesis, the 10% in our example with the proportion, is true when we calculate the p-value. If the p-value is really small, we tend to reject the null hypothesis and accept the alternative hypothesis. That's all you can say. There's no probability. It's just that it's big or small. And it's highly sensitive, as we saw, to sample size. Very, very sensitive. 7 times higher in some places to the sampling. And it's not true that the p-value is a probability of any observed difference. It just isn't. It's just a chance selection of observations from the target population. So there's all sorts of stuff that we can talk about here. Here's Ronald Fisher's notion. If that p-value is below 0.02, it is strongly indicated that the null hypothesis fails to account for the whole of the facts. That's his way of thinking. Not a bad way of thinking, just his way of thinking. There's other people, Jeffries and others, use other things, compel this, compel that. I would say, yeah, stay out of that discussion and then ask the question, how is it, who are the people going to consume my analysis? What are they looking for? And if they're looking for how likely an idea is, a conjecture, an hypothesis, a theory, given the data, well, you know you're talking posterior Bayesian analysis, which takes evidence, and that's probability of the data given a particular hypothesis. That's evidence of that hypothesis, and times both that and how probable the hypothesis is in the first place, and then you're standardizing that, normalizing that on the expected value of all that data given all the hypotheses. That seems to be a reasonable way to count how obvious or not obvious the number of ways our hypothesis seems to be true. Okay, that's plausibility. It's a logical score, if you will. So we can go through and redo all of these. Try your hand at this instead of the SpaceX rockets. Consider the use of the Poisson distribution. Okay? I think these are really good ideas here. So I'm going to leave you with that at minute number 55. Thank you for your kind attention. See you in the next episode. Be sure to take care of one another while it is still today. And with that, I leave you amongst yourselves. Till the next time. Bye.